Okay, let's do some math. Here's our first double cosine. They gave us the angle. I'm going to go ahead and use the formula that only uses cosine. Remember, there are three formulas. One of them had cosine and sine, one of them just used sine, and one of them just used cosine. So they gave us a cosine. Let's make this really easy on ourselves and only use the one that has cosine. In place of cosine alpha, I'm going to put radical 3 over 2. We do order of operations, so that means I'm going to square what's in the parentheses first. When you square a square root, you get the inside, and then 2 squared is 4. If you like, we can go ahead and cancel this, reduce it, right? That's 3 over 2. We need a common denominator. We get an answer of 1/2. If we're in quadrant 1, what angle has a radical 3 over 2? It'll be 30 degrees, all right? If I double 30 degrees, that's 60 degrees. Cosine of 60 is 1/2. Okay, so if you're really good at unit circle, you can kind of pick some of these things off quickly. But don't worry about that. We showed you the formula, no big deal. Go to the same problem again, but with a different formula this time. Ideally, we would only, since we were only given cosine, we use the equation or the formula that had cosine. Okay, so recall that cosine of alpha was radical 3 over 2. So if we're going to go ahead and use a different formula, we need sine. And so to find the sine, we would do as before, right? We set up the alpha. This is the adjacent. This is the hypotenuse. 2 squared minus radical 3 squared. 4 minus 3 is 1. So I get sine of alpha is 1 over 2. So for example, I could use either one of the other equations. I'm going to go ahead and just use a cosine squared alpha minus sine squared alpha. Because it's simple enough, I don't have to do anything fancy. I have a radical 3 over 2 squared minus a 1 over 2 squared. This ends up being 3 over 4 minus 1 over 4. That's 2 over 4, and that's 1/2. Which we know the answer is 1/2 because that's what we got in problem 10. But I wanted to show you that it doesn't matter which formula you end up using, you get the same correct answer anyway. So the nice thing about cosine 2 alpha is, as long as you know how to do math, you're going to get the right answer one of 3 different ways. Why is it called a double angle formula? So this time we want sine 2 alpha. So sine 2 alpha is a bit trickier. Okay, sine 2 alpha, if you recall the formula, is 2 sine alpha cosine alpha. So you have to have both of them. We did this last time, remember? So this was a 1, Pythagorean theorem. So I know the sine of alpha was radical 3 over 2. Cosine of alpha is 1 over 2. We go ahead and plug these in. I'm going to cross out these 2's, and I get radical 3 over 2. So the difficult part about this proof is knowing which one to use. Now, this is no big deal with the sine 2 alpha, because there's only one equation for that. That's going to be 2 sine alpha cosine alpha. There was a minus in front. There was a times cosine at the end. It's a proof, so we do the left side first because it's the ugliest side. Over here, I'm going to bring in the sine alpha, because we're not going to do anything with that. But this cosine 2 alpha becomes a bit problematic because it could be expressed one of 3 ways. And so we have to decide which one will be the most convenient for us to use. I'm noticing that over here, I'm going to get cosine squared. So I'm thinking that I'm going to want to use the one that has cosine squared in it. So instead of cosine 2 alpha, I'm going to put 2 cosine squared alpha minus 1. Your ability to be comfortable in moving back and forth between double angles and regular, like we're doing right now, is very important in calculus. You're going to need to be able to go back and forth between them. If I go ahead and distribute these, then bring down the rest. And by the way, I have 2 cosines, so that's cosine squared with a sine alpha I'm going to put at the end. You'll notice that this is a minus 2 cosine squared alpha, sine alpha. This is a positive 2 cosine squared alpha sine alpha, and they cancel out. And I'm left with a negative sine alpha. Wow. Problem 14. This gets fascinating. Give the exact value of sine 15 without using the unit circle. So there's no decimals, there's no calculators, this is exact. Well, Recall that the unit circle has 0, 30, 45, 60, 90, etc. We have a few new formulas, right? We have double angle formulas, and then we have the sum and difference formulas. Now, mind you, there is something called a half angle formula, but we're not going to get into those in this class. Okay, they are rarely, occasionally used, rarely, so there wasn't any need for me to really expound on that. However, the double angle formulas are used a lot, and so are the addition ones. So may I suggest to you, could there be possibly a combination of two angles on the unit circle, right? 0, 30, 45, 60, 90, etc. Any combination of two angles on the unit circle that might give me 15 degrees. Well, obviously addition will give us more than we need, but if we end up subtracting, that might work out. If you notice on the unit circle, if we use 45 degrees for angle A and 30 degrees for angle B, we would get sine of 15. Now, of course, it's not that simple. I mean, it is, but it's not. So the formula for the difference of two angles and the sine of it is going to be sine of A cosine of B minus cosine of A sine of B. In other words, if A is 45 and B is 30, that's what we're looking at. Now you'll need to look at your unit circle and give me exact values for these. So for example, sine of 45, that's radical 2 over 2. Cosine of 30 is radical 3 over 2. Cosine of 45 is radical 2 over 2. And sine of 30 is 1/2. Again, you must use your unit circle for these. You have to use the actual fractions. Multiplying radical 2 and radical 3, I get radical 6. 2 times 2 is 4. Radical 2 times 1 is radical 2. And the denominator again is a 4. That's nice. So we can actually write these out underneath 1 denominator of 4. So to answer the question then, sine of 15 degrees is equal to radical 6 minus radical 2 over 4. That is the exact non-decimal correct complete answer using the unit circle and using the difference formula for sine. Let's simplify the following by using the correct double angle formula, and then we use the unit circle to give the non-decimal exact value. So you'll notice that this looks a lot like 2 cosine squared alpha minus 1. So what I'm proposing to you is that alpha is 105 degrees. But where does this formula come from? Cosine 2 alpha. So if we're saying alpha is 105, alpha is 105. 2 times 105 is 210 degrees. This happens to, by the way, be in quadrant 3. Look at your unit circle. What is the cosine of 210 degrees? Negative radical 3 over 2. All right, your final summary for the semester and for the class of Math 135. How is the unit circle helpful with these types of problems?